Today we're going to show you two more examples of electrostatics problems involving forces. Let's say we have two charged metal spheres. We remove some electrons, so the one on the left has a positive 2 microcoulombs, while the one on the right has a positive 3 microcoulombs. Now we can put these any distance apart. So for this example, they're going to be 60 centimeters apart. As we have seen in the other example problems, we could now calculate the force between the two spheres. Both of them being positive, it would be a repulsive force trying to push them apart. But let's make this problem a little more interesting by adding an electron exactly halfway between the spheres. Looking at this quickly, the electron here wants to be pulled towards sphere A, and it also wants to be pulled towards sphere B. Since they're equally distant apart, sphere B with a larger charge should win. So let's see what the calculations tell us. The net force on the electron is going to be the sum total of all the other forces acting on it. In this case, force A plus force B. Now, we'll worry about the directions later. First of all, we're going to figure out the size of these forces. So, the force from sphere A in size is going to be coulombs constant times the charge of A, the charge of the electron, all over the distance between the two. As you recall, coulombs constant's 9 times 10 to the 9 Newton times meters squared over coulombs squared. Now we're going to multiply that by 2 microcoulombs, or 2 times 10 to the minus 6 coulombs, times the charge of the electron, which is negative 1.6 times 10 to the negative 19 coulombs. All of that is over 30 centimeters, so I have to convert that to meters, or 0.30 meters squared. Once again, all the units that we want to cancel out. Plugging in some numbers, the force from sphere A is going to be 3.2 times 10 to the negative 14 newtons. Now, sphere A wants to pull that electron to the left, so I'm going to give it a negative to give us the direction for this force. Now I need to calculate the size of the force from the second sphere, B. I'm going to use the same formula, so it's 9 times 10 to the 9 times 3.0 times 10 to the negative 6 coulombs times the charge of the electron, all over the distance, which again has to be in meters, and then squared. If you plug this into a calculator, you get 4.8 times 10 to the negative 14 newtons. Now sphere B wants to pull the electron to the right, which is the positive direction, so I'm going to give it a positive sign here. So force B is in the right direction, force A is in the negative direction. So the net force on that poor electron is going to be equal to the force from A plus the force from B. Now they're vectors, so we have to keep in mind the direction. So this is negative 3.2 times 10 to the minus 14 newtons plus a 4.8 times 10 to the negative 14 newtons, which gives us a positive 1.6 times 10 to the negative 14 newtons. So the electron experiences a net force towards the right. Now, times 10 to the negative 14 seems like a very small force, but keep in mind that the mass of the electron is extremely small. It's 9.11 times 10 to the minus 31 kilograms. So we can use the F net equals ma to figure out the acceleration of this electron. So the acceleration is going to be the net force that we just calculated divided by the mass of the electron. So we have 1.6 times 10 to the minus 14 newtons all over 9.11 times 10 to minus 31 kilograms, which gives us a surprisingly large acceleration of 1.8 times 10 to the 16 meters per second squared. Now, if this surprises you, it's because a coulomb is actually an awful lot of charge, and electrons are very small, so they can be moved around pretty easily with electric fields. So to summarize, we had to figure out the net force, and in this case there were only two forces, so I bypassed drawing a force diagram. We had to find the size of each force, which we did over here, using Coulomb's law. Then we applied the direction, knowing that opposites attract. We had to decide that left was negative and right was positive. Adding those up with the correct minus sign gave us the net force. Then we took the mass of the electron, and using Newton's second law, F net equals ma, we were able to find the acceleration. Electrostatic problems are very much like the force problems you've seen before, except now we have a plus or minus charge. So keep in mind that opposites attract, and always double check that your forces are in the right direction.